So in this chapter is still a very important chapter. It consists of 1/3 of the whole material. Okay, consists of 1/3 of the material, so it's pretty important. So in vector calculus, comparing to derivatives and integrals, we probably have to start even harder. Okay, because if you remember in derivatives, the computation is pretty much the same in single variable calculus. Integration, the calculation is still the same in single calculus, in single variable calculus. It's just that we have to do one extra step, which is to identify the domain. Right? That's the key part for integrals. For vector calculus, I believe a lot of the materials is new to every one of you. Okay, so we have to not only learn the concept, but also the computation. So we want to know what is vector. Actually, we're going to do vector calculus on vector fields. So we have to know what vector field is. In terms of calculus, if I ask you what is a calculus? If I ask you what is calculus? At least in this sequence, what is calculus? Basically, it's just derivatives and integrals, am I right? There are two main pillars of calculus. You have to know how to take derivatives, you have to know how to take integration, am I right? All the things we have been dealing with are functions. No matter it's a function of one variable or function of two or more variables. So if it is a function, we know there is a variable, we know how to take derivative, we know how to take integration, right? But how are we going to do calculus about vectors? How are we going to do calculus about the vectors in terms of how I'm going to take derivatives? How am I going to take integration? Right? So that's the key part for this chapter. We're going to have to introduce what a vector field is and how to do derivative and integration. And the other part about calculus, after we learn about integrals and derivatives, we can connect these two concepts together by the most important theorem in calculus. It's called what is the most important theory in calculus? Fundamental theory of calculus. It's called fundamental for a reason, right? So fundamental theory of calculus. It basically says if I'm taking the integral of a function f dx, it is equal to the difference between the two boundary points from a to b of the antiderivative function, right? Here, so capital F taking the derivative is going to be equal to small m. So this is the fundamental theory of calculus. Fundamental theory of calculus is very neat and very concise if you have a function involving one variable, all right? So I never asked you this question before, but if I ask the question right now, after we learn about derivatives involving multivariable and integration involving multivariable, what is the fundamental theory of calculus if you have more than two variables, two or more than two variables? If you think about that, that's not an easy question to answer. All right? It is definitely not an easy question to answer. For instance, if I'm taking the double integral, I have to specify the domain. All right? How am I going to relate the double integral in a domain or a region in the R2 to some function related to boundary, right? So A and B are boundary of these integrals in one-dimensional space. But if you look at a double integral, your domain is going to be a region in R2, and a boundary is going to be a curve, all right? So if I have a domain in R2, so this is my intervening domain R. Okay, so if we're looking at double R f x y dA, so this integration is with respect to a domain in R2. So I have a domain in R2, and the boundary is going to be a curve. In one-dimensional class, this is an interval. An interval from A to B, the boundary are 2 points. So pretty easy and concise, very neat. The fundamental theory of calculus in one single variable is the easiest, but in two variables is already very challenging because I have to describe what my integrating domain is and what the boundary is. All right? So this can only be explained by using vector calculus. So vector calculus is, for one, we have to know how to take derivative and integration with respect to vector fields. For two, we can generalize fundamental theory of calculus from one variable case to multivariable case. So we have two big objectives right here. Okay, so after this chapter, after this whole semester, you should be able to do derivatives involving more than two or more than two variables. You should be able to do integration with two or more than two variables. Not only that, you should be also be able to explain how to link these two, integration and derivative. Okay, so that's the whole goal here. So chapter 15 is called vector calculus. So we have to know what a vector field is. Have you heard about this vector field before? So in linear algebra, some other calculus 2 vector field? No? Okay. So if you haven't heard about this before, do not get scared. This is a pretty easy concept. Nothing fancy here. So a vector field is a function, okay? It has two components, the x component and the y component. So basically, a vector field is also called a vector function. Okay? It's also called a vector function. A vector function involving two independent variables. So that's why I have a little arrow here. Okay? It says it has two components. F component is defining the x, and G is defining the y here. So we also have this very popular notation here. Okay. So this is another equivalent notation. So this is also denoting a vector field. So a vector field should be understood in this way. Okay, so vector field should be understood in this way. If I put in a pair of numbers as x and y, I'm getting a vector out. That was me? That was me. So basically, every point x, y in R2 through this vector field, you're getting a vector. Right? So if you input a pair of numbers, according to these two functions, f and g, I should get an x component, y component, and then in the end, I'm getting a vector. So if you find these vectors at different points on R2, you're getting a field of vectors, right? So that's why it's called a vector field. Okay, you're getting a vector at every single point. So if you find more and more vectors at different points, in the end, you group them together, you're getting a family of vectors, and that family of vectors is called a vector field. So I'll give you a couple of examples. For instance, let's look at this example. F is equal to 3x and y. Basically, the x component is defined as a function equals 3x, and the y component equals 1. Or according to the second notation, this is nothing but 3x times I plus y j. Okay? So the way of graphing the vector field is I'm going to find a list of points on R2. And then at every single point, according to this formula, I find that corresponding vector. Okay? So finding a list of points and a list of corresponding vectors and group them together, that's going to be the picture of a vector field. So let's do it for this simple example. So for instance, I can find, let's just find a couple of them. Should be sufficient to see the big picture here. Okay. So here is the points I find. Let's begin from x, y, and here is the vector field at this point x, y. Okay? So for instance, if my x, y is equal to 0, 0, what is the vector I find according to this formula? I have 0, 0. So it's a 0 vector. 0 vector does not even have a well-defined direction. So it's just a 0. The length is a 0. So if I have, for instance, 1, 0, what is the vector I have? So it's going to be 3 and 0. Okay? 3 and 0. So at this point, I'm supposed to have a vector pointing to the positive direction of x-axis with length 3. Okay, so this is the vector I have. Okay, so for instance, if I have say 1, 1, what is the vector we have?
3, 1.
It's going to be 3 and 1. All right, 3 and 1. So at this point, I'm supposed to have a vector pointing to 3 and 1. So basically, I'm supposed to have 3 here, 1 here. So this is the vector I have. Okay, are you with me? So basically, if you put in a pair of numbers as x, y, anybody is confused here? Okay, so here, according to this formula, if I plug in a pair of numbers as x and y, according to this formula, I'm supposed to have a vector defined by this formula. Are you with me, Ali? Okay, for instance, if I put in x equals 1, y equals 1, according to this formula, I'm getting a vector 3 times 1 and 1. All right, so that's what the vector is here. Okay, so this guy is nothing but 3 times 1 and 1. This is my x, this is my y. Okay, yep.
So when we graph the vector, it's not coming from the origin?
No, it's not coming from the origin. It's always based on the point. And the other thing you can understand about vectors, the base point is not crucial. You can always translate the vectors. But in order to have a clear picture about the dependence of the vector fields on its base points, it's best to put the vector beginning from the point where it is defined. That's me. So this will be pretty clear. This vector is defined according to this point. And this vector is defined according to this point. That's me. Okay, so for instance, I can have, say, 0, 1. What is the vector we have according to this formula?
0, 1.
So it's going to be 0, 1 as the vector. So 0, 1 is on y-axis and is pointing upwards. So this is going to be a vector right here.
So if you found the vector at 0, 2, it should overlap on that vector, right? The one that you already drew?
Which one? 0, 2?
Yeah.
If the 0, 2, I'm going to find the base point at here. And according to the formula, I'm getting a 0, 2, so it's going to be a vector pointing upwards.
So it should
okay.
always...
I see what the point is. Here I have two different notations. If I'm using this parenthesis, I'm saying this is a point. All right? If I'm using this kind of brackets, I'm using as a vector. All right? So this is a point. This is a vector. So they are quite different. Is that what you're asking?
Kind of. I was just asking, like, if you choose a point on an already existing vector, will it just extend that line? Will it just
Well,
keep
it's
following
highly
it?
depending on the formula I have here.
Right.
Right.
Yeah.
So if I choose this formula bit, for instance, I can have this to be y squared or minus y or whatever. I'm just giving one example to graph the vector field. That's all. Okay. So let's say if I move counterclockwise, like if I look at the vector defined by this point, what is that? So it's going to be -1 and 1. So the point is going to be given by -3 and 1. So -3 and 1 is going to be going to this direction. Okay? So let's see what do we have for -1, 0. So if x is equal to -1, y is equal to 0, what do we have? It's -3 and 0. So this is going to be pointing to this direction with length 3. Okay? So let's finish our work by graphing a couple of more vectors here. So if I have -1, -1 as my point, what is the vector we have? It's going to be -3 and -1, all right? So it's going to be pointing to -3, 3. So this is going to be the vector. Okay? So I can easily graph a couple of more vectors based on 0, -1, I'm getting a 0, -1, so it's pointing to this direction. And if it is 1, -1, I'm going to get a vector looking like this. Okay? So I only graphed 1, 2, 3, 4, 5, 6, 7, 8, 9, plus the origin, 10 different points. You can graph these vector fields at more points, and you're going to get more vectors. Right? So more points will give you more vectors, and you graph them together, you're going to get the picture of the vector field. This is basically why it is called a field. You're getting a field of vectors. Okay, so here is a picture of a vector field, and our big question is how is this related to calculus? All right. How is this related to calculus? Before I answer this question, there's a lot of relations between vector field and calculus. I want to draw one more example. So let's say if I have this example, f is defined as 2x 2 what? Okay. Let's graph this function. The functions are defined for the vector fields are all pretty straightforward. They're quite easy, linear functions. Here at 3x and y, here at x 2y. So graphing them should be pretty easy. So let's say I still have these sample points. I want to graph the vectors according to this formula. So this formula is given by 2x, 2y. So we can easily find these vectors according to different base points. So at 0 is still 0, right? At 1, 0 is going to be 2, 0 as the vector. So I'm going the same direction as x-axis and go for 2 units. Okay? So at 1, 1, I'm going to get a vector 2 and 2. So basically, it's still going to this direction for 2 and 2. That was me? And at this point, it's going to be 1, 0. So according to this formula, I'm sorry, 0, 1. According to this formula, it's going to be 0, 2. So it's pointing upwards. And this is going to be pointing opposite to the radius. And this is this one, this is the other one, and this is going down, this is going the other direction. Okay? So this is going to be the picture for this vector field. And this vector field is pretty special. It's actually a radial vector field. It's called radial for the following sense. If I line together between the origin and the base point, if I line these two together, then the vector defined at this base point is in the same direction as the radial direction. Now with me? It's at the same direction as this radial direction. So this is why this vector field is called a radial vector field, because at every base point, you're just getting a same direction as the radial direction if you line the base point with the origin together.